Yes.
Okay, good.
Oh.
So our next speaker is Andrew Tolley. He will tell us about effective field theories and positivity bounds. Let's welcome.
Okay, thank you. So I hope the technical problems stop. So thank you. So this talk actually nicely follows on from Zhao's talk. As he mentioned, what I'm going to talk about is the positivity bounds, which is use less information than the full bootstrap. So the key difference is that it's positivity rather than your full unitarity. So we only use positivity effectively of the imaginary part. So it's weaker assumptions going in. There are some advantages to that, though, and one is that you can get farther analytically with those assumptions. So I'm not going to less rely on numerics, and this approach is more suited to analyticity. So the rough story you're probably familiar with. The basic question that people are asking right now is, are all effective field theories allowed? Sometimes this is called sort of the difference between swampland and landscape in the string literature, but really it's a sort of old question that's got nothing necessarily to do with string theory. And the key modern recognition is that, you know, if you make assumptions, which are quite reasonable assumptions, such as locality, causality, Poincare invariance, and unitarity, then not all low energy effective theories can be UV completed with those precise assumptions. Now, in fact, just to sort of intro this a little bit more, I'm going to take a step back even from the S matrix and just talk about this at the level of the two-point function, because you see all the features there already, and I think it's quite nicely illustrative. So if you remember that in your standard quantum field theory course, you're introduced at some point to the two-point function in Minkowski space, in the Minkowski vacuum of some scalar operator. And there is a well-known result called the Challen-Lehmann spectral representation that if you look at the two-point function of an interacting theory in the Minkowski vacuum in momenta space, its structure has the form where typically there might be a pole part, there may be some subtraction polynomial you need depending on the growth of the imaginary part of the two-point function. But in general, you can write it as a spectral integral, spectral distribution over the so-called Challen-Lehmann spectral density rho, which has to be positive by unitarity. And so you can prove this, but that this has to be true based on the principles of locality, Lorentz invariance, and unitarity. So this is the most immediate consequence of those basic assumptions. And it also immediately ties into the analyticity story, because when you work in complex momenta, so if you think of the I epsilon in the Feynman propagator as just part of a complex momenta squared parameter Z, then all the Challen-Lehmann spectral representation is a statement about the analytic structure of the two-point function, namely that it has a pole and a branch cut, which lies on the physical region, so it's 4m squared and then to the right. And it's otherwise analytic everywhere, modulo some number of subtractions to write that dispersion relation down. So this, of course, all sounds very familiar. It's what we use in the S matrix. Now, when we now apply this with the concept of effective field theory, in effective field theory, what can we do? We only know the theory at low energies. We don't know what the UV completion is. So from an analytic point of view, what it means is we can effectively compute stuff in some region whose size is of order the cutoff of the effective theory. That's where we actually know what's going on from the effective field theory point of view. But if we don't a priori know what the UV completion is, we don't know what's going on out here. But the fact that we can compute stuff in this region means that we can subtract it out and move the position of the branch cut out to the right. So explicitly, if I take the two-point function and I subtract out the pole part, and I also subtract out the low energy part of the cut, which again, we can calculate that because that's within the region of the low energy effective theory, I can push the branch cut all the way out to where the cutoff of the effective theory is. But I know I should still have something, after I've done that, I should still have something which is analytic. I just don't know what it is. So I have no idea what rho of mu is at energy scales above lambda, because that's beyond my effective field theory. I don't know anything about that. But what I do know is that whatever it is, it's analytic, and it has a positive spectral density. And that's the sort of starting point then of deriving the positivity bounds, because now you can see very simply, if I expand this in powers of z, and I differentiate, so equivalently, if I do the Taylor series or differentiate it and evaluate it at z equals 0, and I have to differentiate enough times that the subtraction polynomial drops out, because that's the part I can't determine. But ignoring that point, all the coefficients in the Taylor expansion are given by integrals of this form over a positive density of some power of mu, and they're obviously all positive. And these are the so-called, what I would call the linear positivity bounds, the ones that actually mostly people have used till recently, simply come from that clear positivity. So it's obvious that all these integrals dm are positive. You can make some other statements. It's also obvious that dm is bigger than lambda squared times dm plus 1, because if I increase m by 1 and the integral starts at lambda squared, it's obviously going to be suppress it by at least lambda squared. And so you have various bounds. But these are all the linear bounds. This is by and large what people have been doing till very recently. However, more recently, people recognized or rediscovered, I should say, that there are nonlinear positivity bounds. In fact, this was already done in the 1970s, applied to scattering amplitudes, funnily enough, but you have to work hard to find the literature. And the key recognition is that if I take these quantities, of course, I can think of that as like a moment of some probability density. I can think of it as an expectation value of 1 over mu to some power. Now, if I consider these various Taylor coefficients and sandwich it with some real parameter y and sum over them, I can rearrange it so it sums into a complete square, which has to be positive because it's an average with a positive moment, positive density of something that's a complete square, so it's positive. Therefore, this object, if I view this in matrix language, this matrix contracted with the vector and its transpose is positive. Well, that means at least the determinant of that matrix is positive. And this is this famous, well, now famous positivity of this Hankel matrix, which is used in the HEFT hedron story. But as I say, it was actually recognized already in the 1970s. So a simple example of that is one of these bounds just comes from, say, Cauchy-Schwarz, which is just whenever you have a 2 by 2 version of this matrix, the determinant of that matrix has to be positive. Now, these bounds are obviously nonlinear because the determinant is a nonlinear function of those parameters. So just to give you a taste of then how this relates back to, this is probably obvious to most of you, but how this relates back to the effective theory itself. So for example, I suppose we were doing this for a tree-level effective theory of some scalar field that we've got by integrating out some physics. So you'll have all sorts of high derivative corrections in the effective propagator. So the tree-level Feynman propagator would look like something like this. And so the procedure you do is if you assume, for example, no subtractions are needed, just for simplicity, then what you do is you subtract out the pole part and then re-Taylor expand. And these are then your coefficients from that process. And so then the bounds give us various things. So for example, this Cauchy-Schwarz bound tells me that this coefficient times this coefficient is bigger than this coefficient squared. That ends up just reducing down to this nice elegant formula, 1a3 minus a2 squared is positive. The next one is this one times, say, this one squared is, sorry, this one times this one squared is bigger than this one cubed. That's another one of these bounds. If you combine that with one of the linear positivity bounds, you get another simple statement like this. So they all have this kind of determinant-like structure, but there's an infinite number of these things you can derive, and that's sort of the more recent part of the, say, HEFT hedron story that people recognize now. Okay, so when you go apply this to the scattering amplitude, it's really the same story. The only new feature is that because of crossing symmetry, SU crossing symmetry, you have a crossing symmetric branch cut going to the left and a crossing symmetric pole. But otherwise, the story is the same. You write the scattering amplitude is an analytic function in the complex plane, so it has its pole contributions, which I've written explicitly here. It has in general some number of subtractions, which if you assume the Poisson bound is valid, or the non-zero t extension of that there's only two subtractions needed, it looks like that, where these are functions of t. And then you have your right-hand branch cut and your left-hand branch cut contributions. Now, you can play the same game, that you can remove the effect of the low energy loops to get rid of annoying logs at low energy and so on, and shift the branch cut up to the point of the cutoff of the effective theory. And that's always better to do, so that you don't, otherwise if you don't do that, your positively bounds are always get too contaminated by the IR loops. But if you move the branch cut, then it gets rid of that part. And then you get a nice clean analyticity statement. You can then do the same trick in expanding. So for example, this is well known by now, but if you just do all the S derivatives of the scattering amplitude, if I evaluate it at the crossing symmetric point S equals 2m squared minus t over 2, then you get a nice simple formula where there's essentially, so that's supposed to be U actually. So you get what's on the top is now the imaginary part of the S channel branch cut, which is the right-hand one, and the imaginary part from the U channel, so that comes from the left-hand branch cut, both of which of course are positive, and the denominator is just some power. And so again, this is like a moment with respect to a positive distribution, and obviously has to be positive. So that gives you your linear bounds, and as well as it being positive, you also have these nonlinear bounds which come from the determinant-like condition. Although technically speaking, you can only, this formula only valid for even m. So you take the determinant of only the even combinations, but that works for any t, positive t, from 0 in principle to 4m squared. Or if you're just doing a weakly coupled thing, it would actually go all the way up to lambda squared in practice. These particular bounds are straightforwardly extendable to general spin. I won't mention too much of that, but in the case of massive, there is one difference with massive states in the spinning case, is that crossing symmetry is nightmarishly complicated for massive states in the helicity formalism. It's simple in massless, and so if you look at massless scattering, you can sort of avoid the problem. But in the massive case, it's horrendously complicated unless you use the transversity formalism, which essentially diagonalizes the crossing relation in a very simple way. And if you use that appropriately, then you can write, it's straightforward to write dispersion relations for massive scattering of massive states, which have all the same properties as the scalars. So the branch cuts are in the same place, etc., etc. So I won't go too much on about that, but so some of the more recent progress that was alluded to earlier is then combining these nonlinear bounds together with full crossing symmetry, triple crossing symmetry. And so the starting point, as always with these things, is you start with the partial wave expansion. Here I've written it in d dimensions, so these things are Gegenbauer polynomials. So I just write the scattering amplitude in d dimensions in terms of its partial wave expansion. Positivity relies on the positivity of the imaginary part of the individual partial wave. So every individual partial wave has a positive imaginary part. That's all the information we use, unlike the bootstrap approach. So we can define analog spectral density or probability density like this, which is positive, and define moments with respect to that. So essentially taking, given a quantity x, I average it with respect to this spectral density by integrating over all the mu's and summing over L's. Now, so that's the new feature now. Of course, we have it for every partial wave. So as well as integrating over a range of energies from 4m squared to infinity in general, we're also summing over the different partial waves, but it's still a moment, right? So it's the same logic applies. In particular, if we just say, look at the S derivatives of the amplitude, the things we discussed earlier, those S derivatives, which in this notation here, just this F2N0, these are just positive moments with respect to this distribution, and therefore they satisfy the relation I made earlier. Now, the key extra ingredient is that the normal partial wave expansion, or the normal dispersion relation, I should say, only manifests SU crossing symmetry. So we have the right-hand branch cut, we have the left-hand branch cut. So it's all obviously SU symmetric, but it's only valid in a range of T. So the dispersion relation that we have can't be taken seriously for large T and small t, which is why there is no T-channel branch cut built into it. It's not included in that formula. However, you know deep down that you should also have ST crossing symmetry. That should also be true there. So this is particularly simple in the case when you have a theory with a mass gap, there is always a region, the so-called Mandelstam triangle, where a dispersion relation written in SU variables should match a dispersion relation in ST variables, and you can equate them. So if you view, just for technical simplicity, the massless theory as a limit of the massive, just to get around that problem, then you can, by equating the scattering amplitude as a function of S and T with what it is when you switch T and S, which again, the dispersion relation doesn't manifest, you can infer non-trivial constraints that follow from crossing symmetry. So of course, there's nothing new about this per se. This was all known in the 1960s or whatever. But the key point is now feeding that information back in. So for example, if you take this difference and you expand what you've got in powers of energy, so that amounts to expanding in powers of Mandelstam invariance, the first non-trivial constraint you get from crossing symmetry is that this particular average of this polynomial in partial wave L divided by mu squared is equal to 0. Okay, so crossing symmetry tells you that certain averages of polynomials divided by powers of mu are equal to 0. That's the general consequence. This paper by these guys called it null constraints. I'll use that language. So these are null constraints, but they just follow from crossing symmetry. Certain things are 0 by triple crossing symmetry. So the sort of new thing then is to say, well, we can feed that information back in to the partial wave expansion. The usual positivity bounds that we derive don't use that information. What happens now if we feed that back in? So for an example, just to illustrate this as an example, this object here is basically the double S single T derivative of the amplitude, and this is the double S derivative. So as an exact result, written in this language, you can show that the ratio of those two things is related to this particular moment here, and this piece as well. So particular moments. And if you use one of these nonlinear bounds, so just really this is the simplest one, the one that follows from Cauchy-Schwarz. If you square that combination, because it's obviously true that the average of quantities squared is less than the average of that quantity squared. If you square that and rewrite it like this, then you get a bound that is less than equal to the average of the thing squared. And that gives you a higher order polynomial. So when you square it, you get a higher polynomial, which is higher order powers of L. But then what you do is you feed back in the crossing constraint, because the null constraint tells you precisely that that particular a polynomial in L to the 4 averages to 0. And therefore, I can use that information to get rid of the L to the 4 that I've got here, feed it back in, and turn it into a polynomial with only L squared. So I reduce the order of the polynomial in L. And then with a little bit more elementary manipulations, you can show that basically that quantity here that was on the left-hand side, that thing squared is bounded, is less than something proportional to itself. And if you rearrange that, what that tells you is that this quantity F01 is bounded from above and below. So, so this is a key ingredient. Once you feed in triple crossing, the full crossing symmetry, then the positivity bounds don't just tell you things are positive, they tell you things are positive, that they're bounded from above and below. Now, we had bounds like that before in the case of higher spin things, because you've got different polarizations. So you can bound Wilson coefficients from above and below. For example, you can do that for massive gravity. But now this works actually for scalars themselves. And very similar results arrive in the bootstrap, because it uses sort of the same idea. Although here we were able to, this is not the strongest constraint, but this is something we can obtain analytically by these arguments. So one immediate consequence of that is that this rules out a class of low energy effective theories that were not ruled out by the linear positivity bounds. So specifically those theories where you have a soft behavior for the scattering amplitudes. The most famous of those is the Galilean theory, where you have an extra global symmetry. I should have written it down, but the Galilean symmetry is where you take pi, you shift it by a constant. Well, that's the normal sort of Goldstone-like shift symmetry, but you can also shift it by something that goes like v mu x mu. Now, it's well known that that Galilean symmetry restricts the dominant interactions. The leading interactions are these so-called Galilean interactions, which come from a particular antisymmetric double Levi-Civita structure. And the Galilean, the purely massless Galilean is arguably ruled out. In fact, it goes back to the famous Adams et al. Paper. They ruled out the cubic Galilean by positivity bounds. But if you break that symmetry, the linear positivity bounds don't rule out such theories. So for example, how would I break it? I could give the Galilean a small mass, or I could add a little d pi to the 4 term. Both of those terms break the Galilean symmetry. But if the coefficient is small, right, so if this parameter is much less than 1, it's a weak breaking. So I still have approximate global symmetry being true. So naively, you might say, well, there's nothing wrong with that. If I just slightly break the Galilean symmetry, positivity bounds is still, the linear positivity bounds are still true. Well, that's no longer true for these full triple crossing symmetric bounds. And that's very simple to see. And that is because if you compute the scattering amplitude, for example, for the massive Galilean in these theories, what the Galilean symmetry does is it suppresses, it makes the behavior soft. So if you write it in terms of the two Mandelstam invariants, crossing symmetric Mandelstam invariants, s squared plus t squared plus u squared, I'll call it x, and stu is y, then if you have exact Galilean symmetry, this first term would be 0. It's broken by mass, it's broken by pi to 4, but otherwise it would be 0. So a weakly broken Galilean symmetry tells you that this coefficient is suppressed relative to all the others. It doesn't say that the others have to be small. It just says that the first one has to be small. That's the consequence of the Galilean symmetry on the scattering amplitude. But that first one is the thing that dominates what I've called here F00, which is just the double S derivative of the amplitude. Whereas the second one dominates what's called F01, which is the second S and first T derivative of the amplitude. But we already know now that this coefficient is bounded from above and below exactly by this coefficient. So if this thing is suppressed because of the Galilean symmetry, then this has to be suppressed as well. And therefore, we're not really dealing with the Galilean because this piece is never suppressed relative to that one. So in other words, there is no weakly broken Galilean theory, which is consistent with these extended version of these positivity bounds. Now you can play various games with this, and at this point it sort of depends going forward, how numerical you want to be and so on. If you, the particular way we did it was, well, roughly speaking, this really is a cartoon of it. But if you write the scattering amplitude in terms of these two variables, so W is basically SU and T, and do an expansion, define these coefficients here. What we did is then you can use further information from the fact that these are moments with respect to now mu and L. You can use a trivial observation that if you have a polynomial in L whose highest power is positive, then that's obviously bigger than its minimum. And so we have a simple positivity bound that if you take an average of something like this with a polynomial, it's bigger than its minimum. And that reduces, the right-hand side has lower, obviously, because it's the minimum of that polynomial, it fixes a given value of L. And in general, lowering the value of L lowers the number of T derivatives and so makes the bounds more useful. So you get bounds from that, and then you get bounds from feeding back in these triple crossing constraints or the null constraints, because they also amount to some statement that an average of some polynomial in L is equal to 0. So I can take expressions like this and add 0, doesn't do anything, but analytically it changes the form of the polynomial and therefore changes what you can infer from the bound from that. So feeding back the crossing symmetric constraints allows you to derive all sorts of bounds. And this is just illustrative from the paper. these coefficients defined in this expansion, you can derive analytically, if you like, all these different bounds on their values. And this is pictorially represented here. The red bounds and the blue bounds come from different starting assumptions. But you can see that in general, the application of full crossing symmetry is actually bounding the allowed region of the coefficients in a way that the linear positivity bounds never did. Now, I think I'm getting to the end of my time. So beyond that, I was going to mention something about QED, but I think because of time, I'm going to skip that and leave you, I'll skip all that, sorry, and leave you with the final story is that positivity bounds themselves, just like the bootstrap, but they're very powerful at putting constraints on low energy effective theories. The positivity bounds have some advantage over the bootstrap in that they're more analytic. So there's basically two new things going on. One is the recognition we have these nonlinear positivity bounds, which come from these Hankel determinants. And the second one is one can feed back in the information from full crossing symmetry into the bounds. And doing that, in fact, the combination of those two things is now putting bounds on coefficients, which are upper and lower bounds, and gives very little range in practice. And these bounds are extremely, in practice, they're very strong at constraining those theories where you may have had either, say, super soft theories where the scattering amplitude is particularly suppressed at low energies because of some extra symmetry, or similarly interacting massive spin theories, say, for example, interacting massive spin 2 theories, precisely because those theories are naturally very non-renormalizable. So if we try and write them down, then they're automatically non-renormalizable theories. So we have significant irrelevant operators which get strongly constrained by positivity bounds. And I think since I didn't hit my last points, I shall stop there and wait, stop for questions.
Yeah, I don't know, maybe the room is frozen again. So let's, yeah, I see Joao has a question. Go ahead. I hope they can hear
thanks,
us.
Andrew. Thanks for the very nice talk. So yeah, my question is a bit about, can we try to merge, like, I think it would be useful to sometime, for example, I think for weakly coupled theories, positivity is the best you can do, right? Unitarity basically reduces to
That's right. Yeah, it's the same.
And I think now you are basically converging to a systematic algorithm, right? This is what you were pointing out at the end, that you can really kind of optimize and find the.
That's right. Yeah.
So that's great. And then I think the next step would also be to really consider interactions, and so there you have to worry about loops that will create more cuts and the nonlinearities. But for example, concretely, do you think you applicate the just positivity applied to the problem I was discussing can give a bound better than alpha greater than 0? I think that should be possible. I don't know if you thought about that.
The example you're discussing, you mean the string example?
For example, just for concreteness, yeah.
Well, it's certainly, yeah. I mean, the bounds when you more carefully include the loops, the bounds already doesn't give you alpha bigger than 0. It gives you alpha something bigger than something non-zero, right? Just the linear bounds already.
Right, but right, that's when you do this game of going to the cutoff and.
Right, that's right. Yeah.
That's okay. Then maybe just one question about that. And this part, I think makes sense physically, but I have trouble with making it precise, because it's always, how do you really control, where do you put the cutoff, and how do you control the error? Because then you have a bound that you. It's not really.
Yeah, so in practice, you have to, obviously you can't actually go to the cutoff because it's if you think of the cutoff as the point at which everything breaks down, you actually need to go sort of 10 a factor of order 10 below the cutoff or something, so that you can still trust your calculations. So and then as you agree that I guess as you're indicating, then some sense that's slightly unsatisfactory because it's a slightly arbitrary scale and there's errors of that order, and so you have to control that. There are other ways that again people did it ages ago. In fact, sort of doing Parde approximations, guesses for the individual partial waves and removing it in that particular way. So I suspect there's probably a better way to do that than just the naive way I'm saying. Because the thing is, in the end, if you don't remove the cutoff in the end, when you're doing a loop theory, and if you don't have a weakly coupled theory, the problem is, you can say you have these infinite number of bounds, but you're kidding yourself, because in the end you're expanding with things like 1/m squared, and so the higher order bounds that coming from more t derivatives and so on just put more 1/m's on the bottom, and so they don't get stronger and stronger. So 95% of what people have done is weakly coupled UV completions, because then there's a sufficient gap that then when you're expanding in 1 lambda. So that's the problem. So when you're doing the interesting case is when the loop is significant, then if you just naively apply most of the bounds, you can't just do a Taylor expansion, because then you're expanding in 1/m, and 1/m is not helpful. Right. So you have to remove, to get an interesting case in a non-weakly coupled thing, you really have to somehow remove that low energy branch cut in a successful way, so that you're not expanding in 1/m, expanding in some higher energy scale. So the simplest way to do that is the way I said, but as you say, then that's slightly arbitrary. So I think it would be nice to have a better way to do that. I mean, I guess in a sense, in a full numerical approach, maybe it's sort of implicitly built in. So when you try and do these analytic things, you have to do that. Otherwise, you're dominated by 1/m. In a numerical approach, I guess you can probably, maybe the numerics takes care of it in some sense, because you're not trying to get an analytic statement.
Thanks, Andrew. We have to think about it. I think.
No, I think this is actually a sort of crucial thing that I think then so what hasn't sort of been fully dealt with in the positivity approach, which you deal with crossing symmetry, and you're by just explicit, take an expansion which is crossing symmetric, but of course you're making then an assumption and so on. For us, it's a little bit harder to impose crossing symmetry. So ideally, there are some conjectured, well, not conjectured, you can write down crossing symmetric dispersion relations, fully crossing symmetric dispersion relations, but their regime of validity is actually very small. They only really work well in a theory with a mass gap. You've got a very, very small region, and then you can work in that and do it, but then you can't use them for the massless cases. So I actually don't know how to write down a fully triple crossing symmetric dispersion relation in a theory without a mass gap. Which again, you don't have that problem because
I assumed it basically. So it's true that I do more assumptions than what has been proven.
That's right.
Anyway, thank you very much. I have to go teaching. Sorry.
Okay. Can you hear me now?
Yes.
Okay, I'm back. Great. Okay, in the interest of time, let's thank the speaker again.
Thank you.
Emmanuel, can you share?
Yeah, I'm here. Shall I try sharing? Okay, is it working?
Okay, so our next speaker is Emmanuel Eddy. So he will tell us about positivity bounds on minimum flavor violation.
Yes. So